Alright guys, today's lesson is going to be one problem only. This is where we connect stoichiometry to the gas laws. So as always, please pause the tape and get this copy down in your notes. Okay, now that you have the copy down, let's break this problem apart. First thing I'm going to do is shrink this because we need a lot of space. So we're going to put this down in here so that we can see it. Okay. Now, how is this problem different than other problems we've done? First of all, they talk to us about the chemical reaction. None of the other problems have really talked about a reaction in this chapter. Secondly, they ask us for the volume of acetylene gas, but they give us our mass of calcium carbide that reacts. So this tells us that we need stoichiometry, and if we need stoichiometry, this also tells us we need to write out the chemical equation. So let's take care of that right now. We've got calcium carbide, which when you look up the charges is CaC2, and we react it with water just like we did in the lab oh so long ago. And we made acetylene gas. And calcium hydroxide. Okay. We do have to balance this. When we balance it, we need just a 2 in front of the water. So there's our balanced equation. Now, we're given the grams of calcium carbide, so this tells us that we need to do stoichiometry in order to figure out our moles of acetylene gas. If we're looking for the volume of acetylene gas, we need to know N, we need our moles. So we take our 2.49 grams of calcium carbide, and we are going to do some stoichiometry. We only need to go to moles. We don't need to go to grams of acetylene. The molar mass of calcium carbide is 64.08. And our mole ratio is 1 mole of calcium carbide to 1 mole of acetylene. When we calculate, we get 0.0389 moles of acetylene. Okay, so now we've got our N, and our stoichiometry is over. Now this problem becomes an ideal gas law problem. So we've got our pressure is 1.01 atm. The volume they give us is what we're looking for. Our mole value we just calculated is 0.0389 moles of acetylene. And our temperature is at 30 degrees. But now they're talking something about the vapor pressure of water. What in the world does that mean? Unfortunately for us, when we collect gases, we have to collect them through water, just like we did in the lab with our combustion lab where we blew up the different ratios of acetylene gas and air. Well, when you collect a gas through water, you also collect some water vapor. So if the total pressure of the sample is 1.01 atmospheres, then we need to subtract out the pressure of the water vapor that's mixed in with the acetylene gas. In order to do that, we need to convert the 31.824 torr to atmospheres. Okay, so we take the 31.824 torr, and we convert it to atmospheres, and we get 0.04817. It's a lot of sig figs, atmospheres. Let's shrink that down. So what that means now is we need to subtract value from our ATM. So minus 0.04817 atmospheres. This will get rid of the partial pressure of the water. When we do this, we get 0.97 atmospheres, and this helps us to keep our sig figs together. Now let's shrink this down. Now we can finally put this into the ideal gas law. So let's do that. We know that PV equals nRT. We're looking for volume, so we're going to divide by the pressure. So we're going to solve this as V volume is equal to nRT over P. And let's just do it. It's a plug and chug time. So V is equal to our moles that we calculated through our stoichiometry, 0.0389 moles. The R value we have to use, we choose based on our pressure unit, and since we're in atmospheres, we have to use 0.0821 liters times atmospheres over moles times Kelvin. And we're going to multiply that by our temperature, which when we add 273 to it, we get 303 Kelvin. And we divide by our pressure of 0.97 atmospheres, and that's just the pressure of the acetylene gas. When we run all of this math, let's see here, we got to cancel out our units. We're left with liters, which is perfect. When we do all of that work, we get a decimal answer of 0.996, and we can keep 2 sig figs, so this is going to be roughly 1.0 liters of acetylene gas. So this is how we go about solving a problem using stoichiometry. Let's recap. The reason why we needed stoichiometry in this problem is because we were given the mass of one of the reactants, but we were asked to find the volume of a product when we are not at STP. Because we're not at STP, we were at 30 degrees Celsius and 1.01 atmospheres total of pressure. Our total pressure was 1.01 atmospheres. We needed to first use stoichiometry to get the mole value of our product, acetylene gas. Then we had to subtract out the water vapor pressure from the system. So we had to convert the 31.824 torr to atmospheres. When we subtracted that out, the vapor pressure, or excuse me, the pressure of acetylene gas only was 0.97 atmospheres. Then we could finally get to the ideal gas law and solve for the volume like we have been doing. These are not the hardest problems, but you do have to break the problems up into smaller little projects before you can solve the entire thing. You have to take your time and you have to read the problems carefully. Have a great evening.